Okay, so our last speaker of today is Theresa Zeman, who is going to talk about skyrmions in bounded domains.
Thank you. Thank you for the introduction. I hope, now, okay. Now I hope everybody can hear me. I didn't take as much care with the title as we did with the paper because, uh, well, the minimizers I'm going to show you, or I'm going to prove exist. We don't know how they look like, so maybe it's a bit misleading to call them multiple skyrmions, but well, that's what we're aiming for. We've already seen what skyrmions are in the first talk. So let me be a little bit brief. I'm a mathematician. I'm going to do a math talk. Um, so just very briefly, the magnets we're considering are extremely thin. So just to give some, I like to give some numbers, although probably uh, people in the audience can correct me if I'm wrong. So we're looking at samples which are atomically thin. So a couple of atom layers. So say zero point 0.1. The films are 0.1 nanometers. The samples are quite wide. So these could be in the hundreds of nanometers. And also we have another length scale in here, which is the exchange length. Uh, which is about 1 nanometer. So the exchange length is the length below which the magnetization likes to be constant. So just from comparing these numbers, you'd guess you'd like to assume that your magnetization is constant in the in-plane direction. In the out of Yes, sure. Okay, okay. Then let's move one up. Thank you. Um, Still, factor of 10. Um, anyway, so the magnetization we're going to look at um, are maps from some domains omega, and these are going to be in R2. I'm going to talk about bounded domains, so I'm not going to write equal R2 here. And those are maps into the sphere, so magnetization just has a direction. Length is a material constant, and we normalize it to 1. Um, and by M prime, I mean the in-plane components. M3 is the out-of-plane component. And in these, also here, a physicist would be able to tell you more. Maybe for these magnets, you find two features that are maybe less typical than what people looked at before. One is they tend to have perpendicular anisotropy, so the magnetization wants to point up or it wants to point down, preferentially. And also there is the DMI that we saw earlier, and both of those lead to the possibility of skyrmions being stabilized. Um, Let me not draw some pictures. Let me not try to draw pictures. You've seen them in the first talk. Uh, I could draw, but that's the downside of Blackboard talks. No nice pictures. And we've also already seen that topology plays quite a big role in these. Um, but let's come back to that later after I've given you the model I'm using. So I'm going to use the magnetic energy in the following form. So E depends on kappa and Q, and it takes as an argument the magnetization M, and I have three terms. First is the exchange energy, just the Dirichlet energy together with the S2 value constraint that turns the problem it has the flavor of the harmonic map problem, and it means it's non-convex. Then we take DMI, and the version of the DMI I'm using is surface DMI, and I'm going to write it down like this. So kappa, I'm going to take positive, but the sign doesn't really matter. There is a transformation that flips the sign of kappa. And I'm going to use perpendicular anisotropy. So this likes the magnetization to point upward, wants it to point down. This, as mentioned before, prefers winding of the magnetization. So this is big if the two vectors point in the same direction. So M3 likes to change in the direction in which M prime points, and you can easily imagine that things like to look like this. Okay, so that's the energy. I'm not going to use any stray field energy. I'm not going to use any applied field. And Q, this is important. Q, the quality factor is bigger than 1, so I have a positive number in front here. Okay. We're on a bounded domain. I'm going to tell you what my boundary data are. For simplicity, I'm just going to take Dirichlet boundary data. So I'm going to encode them in the following. So okay, I want H1 function. So I want, which basically means all these terms make sense. And I want that M is equal to minus E3 in R2 outside of omega. So I artificially extend by minus R3. Okay, I guess I should write this. So it's constant outside of omega. So that's the energy and the admissible, in principle, what I could put in there. Now I need to encode topology. And the way we do that is by introducing the topological charge. We've also seen that one in the first talk. So we integrate over R2 m dot partial 1 m cross partial 2 m dx. This is also the reason why I extended to the whole plane so that I could write down the integral over R2. Of course, if it's constant outside of omega, you get 0 here. So that doesn't contribute. Mathematically, that's a version of the Brouwer degree if you want, and you can prove that this gives you an integer number. And all the things you want to have from the Brouwer degree basically follow from there, plus maybe a couple of explicit computations. So in particular, the degree is continuous with respect to the strong H1 topology, but not necessarily with respect to the weak. And we're going to fight against that later. Okay, now I said we're going to be interested in not just degree 1, but in higher degrees. So let me give you notation for that. For D and N, we say that we define the admissible class AD as the magnetizations like that. H1 homogeneous, R2 values in S2, M equal minus E3 on R2 without omega, and now the degree of N should be D. And we're going to ask ourselves, what can we say? I mean, we're going to ask ourselves, what can we say about minimizers in this setting? Um, let me give you uh, uh, a bunch of things we already know, and most of them. So first, uh, let's go. In fact, let's go to the whole space for a moment, and let's set kappa equal to 0 and q equal to 1. So basically, erase the two terms. That's not what I assumed up there, but it's helpful to think about it for a bit. And there, physicists Belavin and Polyakov in 75, and mathematicians Lemaire in 78, I think, yes, as well as Wood in 74. They identified, well, they came up with this nice topological bound, which bounds the Dirichlet energy on the whole space by 8 pi times the modulus of the degree. And just to be very brief, for those of you who haven't seen this part of the talk before, it looks magical. It is in fact very simple. You insert the definition of the yeah. You take one of the two signs, you insert the definition, and you complete squares. That's it. So that's nice, and that also allows you to. So this is what I'm going to refer to as the topological bound, lower bound. Logical lower bound. And based on the excess in this inequality, which is explicit, you can figure out the equality case. So what the minimizers in this inequality are, and they are, if you use a stereographic projection, if you put a stereographic projection here and go to the complex numbers, you get that minimizers are meromorphic functions. With the appropriate degree. I'm not going, I could write down what they are, but let me only give you the case we really need, which is, yeah. Yes, it's equality. That's also important. Sorry, that might have been just a little bit implicit. For d equal 1, I'm going to write them all down for you because those are somehow our main building blocks. We like to call them BP profiles, Belavin-Polyakov profiles. Mathematician, the mathematically minded people of you might be more likely to call those Möbius transformations. And I'm going to parameterize them in the following way. So the set of them I denote by curly b. So you pick your favorite, you pick one function, and the function I'm picking is a version of stereographic projection. And for convenience, here, it's convenient to use this one. Okay, good. So this points down, it has the correct degree. And then you can do a bunch of things with this. You can rotate this. You can dilate it. And you can translate it. And those are all the minimizers in the degree 1 case. Okay, so that's the whole space picture when you just have exchange energy. Now, let's see what happens if you add the lower order terms back in. And then, so still whole space. But now kappa positive and q bigger than 1. You need both, actually. There, Christoph Melcher proved in 2014 that you have existence of minimizers in a slightly modified version, but never mind. And then, okay, I already said it. Dirichlet energy is so the exchange energy is leading order. The other two terms are lower order. So you can ask yourself, well, what happens if Dirichlet energy dominates? That's called the conformal limit. And that's basically the question of what happens if this combination of parameters vanishes, and there Melcher and Döring in 2017, I think. Yep, they did some preliminary work, and then Anne, Cyril, and myself. This was 21. We figured out what we figured out what the energy does, and here's so minimizers concentrate into points if you want. So the radius shrinks faster than you'd expect. And well, we can describe, in this limit, we can describe skyrmions in terms of their degree of the degrees, or in terms of the degrees of freedom the Belavin-Polyakov profile gives you. So, our limit determines the rotation. It determines asymptotically the radius, and in the whole space, in the whole space, the location doesn't matter. And I'm probably slow. Okay, then I'll just very briefly, because I like this theorem very, very much. So the thing that allowed us to deal with the conformal limit is a rigidity result for the harmonic map problem. And it says that I'm going to be very brief. There exists a universal constant such that for all H1 homogeneous H1 maps from R2 to S2 with degree equal 1. There exists a Belavin-Polyakov profile such that, now I'm running out of space again. Yeah, let me erase this part. We can control the Dirichlet distance of these two things, of M to the chosen Belavin-Polyakov profile by constant times the excess in the topological lower bound, which I hope I just erased. Hallelujah. So then you have Belavin-Polyakov profile around which you can perturb, and you. It's a long story, and I don't want to get into that paper. But what I should mention is that afterwards there were two more proofs, one by Hirsch and Seemas. In 2001, in 21, no, 22, and then Peter Topping in 23. Okay. Now, that's the whole space story. For bounded domains, here we did some work with a former postdoc of Valeri, Cyril, again myself, and Valeri, Slastikov. Up. This was, I didn't write down when this was. I forgot. 24, 23, somewhere around that. So we did existence. So still D equal 1. We did existence plus the conformal limit. Okay. So, okay. And for a long time, every time I gave a talk about this topic, everybody asked what happens for, is there a question? A lot of people asked, well, uh, what happens in higher dimensions? And I'd have to always say, oh, that's an excellent idea. What does happen in in higher dimensions, sorry, and for higher degrees? And well, this is, you know, previously to our paper, we didn't know anything. So the thing about higher degrees is that the whole situation is a lot more complicated, right? I mean, for degree 1 we had single skyrmions, and now for higher degrees, they could, you'd expect multiple skyrmions. They could be separated from each other. You could have, but you could also have, a degree 2 object, or you could have where the degrees kind of happen on the same scale, but you could also have, a skyrmion, and then on top of that, a tinier skyrmion tacked on. And there is a lot more, the model has a lot more flexibility, and it's not clear, which one does the model choose. We still don't know, but we said, well, okay, maybe you should start with existence. Let's at least try to prove that we get existence of these objects. And because, and well, the bounded domains, Dirichlet energy sounds like the simplest way of doing that. If you try to do it, say, on a whole plane, you immediately run into the question of, well, does it like to stay together or does it want to go far apart? Which we don't know yet, at least not on a mathematical level, on a mathematically rigorous level. So let's just deal with existence of minimizers. And because we're the first, we also don't have to, let's see what we can do, right? We don't have to try and be super optimal. We just let's see what we can actually do. And the thing we came up with is the following. Theorem 2, this is now Muratov, myself, and Valeri. This year. Well, the paper was published this year. The preprint is correspondingly older. And the statement is the following. So we have a constant bigger than 0, and this one is universal. Such that if omega in R2 is Lipschitz, D is our target degree, kappa is bigger than 0, and Q is bigger than 1, such that I have a bunch of relationships. The following is that kappa squared divided by Q minus 1 should be less or equal than, oh God, okay. I'm sorry. Should be less or equal than minimum of 2d plus 1 1/2. Okay, so the number needs to get smaller if d gets bigger. That's what I want to take you away from here. And then there's some numbers flying around that we don't have to care about too much for the moment. So that's the same parameter as up there. Right. But we also need we need to know that the domain is large enough. So the area of the domain that we need needs to be bigger than C multiplied by D divided by kappa squared. Then uh, uh, then the energy has a minimizer over omega in a t. I know I can put this up. So if you look at this, we prove a little bit more in the paper, but I'm picking a specific case that I hope makes it a bit easier to parse. So kappa needs to be small, but if kappa is small, the size of omega needs to be quite large. But that's just so somehow the skyrmions need enough size. We do not claim that these conditions are optimal. In fact, I'd be surprised if they are, but that's my feeling. Right. And I already mentioned that in the conformal limit, you expect concentration of skyrmions into points. Dealing with the conformal limit here doesn't quite make sense because, at least as we had it before, because, well, when this number gets, when kappa gets small, omega needs to get bigger. So let's not do that. Let's fix everything instead of kappa and send q to 1. Then you can still, q to infinity. In that case, you can still expect concentration of skyrmions. Well, because you penalize the out of plane components more and more, the in plane components more and more. And then what we can prove is the following. Well, it's first, some natural number, some degree, kappa bigger than 0. For technical reasons, we need omega simply connected and simply connected with a C1 alpha boundary. Such that at least the second condition holds, and then for Qn going having a sequence to infinity, minimizers Mn exist at least for n sufficiently large, and along subsequences, which I'm not going to write down. So we know that the weak limits of these in H1 is just pointing down, and we know that we can say something about the energy measures. So d mu n, which is so we write down the energy density 2 kappa m prime dot nabla m3 plus q n minus 1 m prime squared dx. These converge as measures weakly star to a bunch of Diracs. So from 1 to k, 8 pi dj delta xj, where k is less or equal than n d, thank you, less or equal than d. The sum of the di's is d. These are natural numbers, of course, and the xj's are in omega. I don't remember. Let's say closure for safety. Yeah. Point is, yes, they concentrate, but we don't know with which degrees they concentrate. So we can't say anything about, is it single skyrmions or is it things happening on similar scales or on different scales or whatever. But the XJs could be all. I mean, okay, maybe I should write down the XJs should be that the XJs, should all be pairwise different. But still, then you don't know what the DJs are. Okay. But okay, so we don't, we can't really say much. This is the best we can say about minimizers in some asymptotic regime. So that's the reason why I said that, or in the beginning said that saying I'm doing multiple skyrmions is maybe a bit of a cheat. I'm dealing with existence of minimizers with higher degrees. And right, so those are the statements. Let me give you at least a bit of an idea of how to prove them. And I need some space. Let me, yep, sure. Uh, um, Sorry, say again. Yes, yes. Oh no, I still, where is it? It's an assumption such that star holds. No, 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 I need that. I need that. It's just that, when Q gets large, the first one is boring. Yes, yes. Yeah, yeah, that's the main point. But, the main meta point is we can't do better than this for the moment. Um, yeah, let me get rid of this part again. Oh, I already said these are non-optimal. Therefore, what was this? I have tried and therefore nobody can criticize me. Um, okay, sketch of the whole thing. So I'm actually only going to sketch existence. Um, the concentration part is, finding the correct reference in the literature and applying it. Um, and for the existence, so in degree one, you basically need two ingredients. You need an a priori bound, which in this case boils down to the statement that the energy is bounded from below by 1 minus 2 kappa squared q minus 1 Dirichlet, so exchange energy plus 1/2 anisotropy. Uh, that's just Cauchy-Schwarz. And an upper bound by construction. And if for degree one, this was you had to say that the inf of E kappa Q for degree one is strictly less than 8 pi because, well, if you had a minimizing sequence which concentrates into a point, the lower order terms would vanish. The lower topological lower bound would give you 8 pi, and that rules, that tells you that concentration cannot happen. Um, so that's okay. So you do need some. I mean, you clearly need some upper bound, and the easiest upper bound you could write down is the following. Um, so okay, I need some. Let me introduce some notation for the inf over AD, because otherwise I'm going to go. I'm going to write. It's going to be hell to write down. So an relatively easily obtainable estimate is that if you increase the energy by 1, you get the old energy plus 8 pi. And the 8 pi is the 8 pi from the topological lower bound, by going 1 degree up in the topological lower bound. This is not good enough for existence. And the reason it's not good enough for existence is that it doesn't rule out uh, it doesn't rule out collapse of topology. So imagine, okay, the way proving this works is you say, okay, let me take a minimum, something that has good energy with degree d. So let's say, I don't know, take d equal 3, and let's say, you have 3 skyrmions there, whatever, doesn't matter. The way you get the inequality is you go somewhere else where the skyrmions aren't, and you add, you know, another tiny little skyrmion. And well, if you make the skyrmion small enough, all you pay is 8 pi. Uh, but in the minimizing sequence, if you just have this less or equal here, you know, nothing rules out that minimizing sequences will actually do exactly that, right? So your minimizing sequence might say, okay, let me keep these 3 skyrmions. Okay, I have something with additional degree here, but let's just shrink it away. And this kind of construction with this lower bound cannot rule that out, because that's basically how you did the lower bound. So that's basically how you did the upper bound. So you have to be you need some more refined estimates. And the more refined estimates are that, well, if you go up a degree, you don't have less energy for some reason. That's easy. That's relatively easy to prove, at least under our assumptions with the a priori bound. But the real kicker is here. You need strict inequality up there. If you add another degree, you increase the energy by strictly less than 8 pi. And now this will tell you that the thing cannot vanish anymore. And so this follows from the a priori estimate. And this is a surprisingly subtle construction. No, both of them. I need both. I mean, uh, it. I don't remember you for this. I'm pretty sure you need both. For this one, you just need the first condition. For this one, you need the size of omega to be big. I'm thinking about which part I should drop. Okay, let me go. Let me go answer that question. Um, uh, how does this work? Well, you need a construction, and the construction is I'm not going to tell you the construction because it's multiple pages of, but I'm going to give you the statement. Um, so there exists a small number universal such that if M is is admissible with degree D, such that we have that the average of BRX of the thing that we control by our a priori bound, if this is bounded by epsilon times kappa squared. Then, okay, no, for some x in omega and all radii positive such that Brx is in omega, then sorry. Then I can construct a good competitor. Then there exists M in AD plus 1 such that the energy of M tilde energy of M tilde is bounded, strictly bounded by the energy of M plus 8 pi. And so, you take an optimizer for degree D, you plug this in, you get the strict lower bound. You get the strict upper bound. And the problem is making sure that you can find a point where this condition holds. So the kappa squared, I didn't mention this earlier. The kappa squared is the next order energy scaling. So you'd expect that the energy of M, at least for a minimizer or a near minimizer, is you take out the leading order Dirichlet contribution, then this is bounded by kappa, is bounded from above by order kappa squared. Minus kappa squared, it's negative. So this kappa squared is this kappa squared here. The problem is you want to make this epsilon small. We need, because the main thing you're fighting. So what you want to do is you have your minimizer, and it has some and whatever happens, but you want to find at least one point where where close around the point you don't have a lot of Dirichlet energy and you don't have a lot of anisotropy energy. So it basically, you want a location in which it essentially points down. Your minimizer essentially, your M essentially points down. And then in here you go and you splice in another Belavin-Polyakov. You splice in another skyrmion. And that transitioning from the previous you do a cutoff, you paste it in, and the transition going from the previous minimizer to your new Belavin-Polyakov, that is really quite tricky. And we couldn't do it unless we have a small constant in front of here. And well, okay, where do you get that small constant from? This might remind you of a Hardy-Littlewood maximal operator estimate. We use covering theorems or estimates for the maximal operator, but those need your set to be large. So you get small, you make sure that you find a point where this is satisfied by having a large domain. And that's where these things are. That's where this inequality, the fact that we need omega large that's where it comes from. If you work through the details, you realize you end up with that combination, but let me not. I know. And with that, I would like to close the talk. Thank you for your attention, for your extended attention.
Now we have question for comments and question because expect students to attract.
Oh yeah, sure. From the numerics that I'm seeing is that if two skyrmions are close, one skyrmion eats the other skyrmion. They don't, you know, they don't go into the same location. It's just that one of them shrinks. It's like if they're too close, one of them just vanishes.
Yeah, it's
That's
more
what
complicated than
it's,
attracting and repelling it
yeah.
does. Not like in the vortex case, in the Ginzburg-Landau vortex. It's they're softer objects.
Yeah. So that's what the numerics say. So that's more like repulsion than attraction, would be my answer to you. So in the whole space, so you may ask whether in the whole space case you would still expect existence of higher degree minimizers. I don't think that would be the case. But, well, no proof. Sorry? Symmetric higher degree minimizers?
Those, yeah,
Probably.
at least numerically, those were constructed. I don't know if there is a theory of equivariant
Oh, that might be
solution,
something.
but I imagine it should be fairly straightforward to prove those the existence of those. Yeah.
I mean, existence and stability of a single axisymmetric skyrmion is known. That's work by Melcher and I prob and probably
Well, there
no
was
postdoc by
even
him.
rigidity for equivariant maps were known even
Yes.
long before us, and even in higher degree case.
Really?
Yeah, I think if I well remember.
Okay.
Yes. Yeah. Philip?
Thank you. Very interesting talk. So what came to my mind is the following picture. So here Raf was saying, so there are three players in the game: the exchange, the Lashinsky, and anisotropy, and of course this bounded domain. But so from the point of view of interactions, so anisotropy is a kind of bad guy because it won't have a linear. The Lashinsky kind of good guy because it refers some homogeneity. So, and I've been thinking of, suppose we exclude these both players and let's consider pure exchange. And so we can take, so initially, let's say any degree and infinite size domain. So for simplicity, let it be this, so infinite radius. Okay, and then let's go to infinite things, to finite. So again, so in all the exchange interactions, so what will happen with minimizers?
Nothing. You will not have minimizers.
So they disappear.
They disappear. Okay. For whatever big disk you take, global minimizers disappear.
Matter of fact, any bounded domain with Dirichlet boundary conditions, there are no minimizers of the exchange, a well-known fact.
So
for any degree other than 0.
Okay. Expect, let's say, if I do accurate numerics, so they will shrink more and more and more.
Yes. Yep.
So it means the pressure from boundaries will be so strong, despite they are very far, for example, that it will make it.
I mean, it depends on what you mean by so strong, and since there is no opposing effect, you know, any positive strength means it disappears.
Yeah, it means
it's
strong enough.
Yeah, and you know, anything would do. It's like saying you have anisotropy, but no DMI.
So and from theoretical
Tomorrow,
and bounded domain, as you
Right,
said,
chapter two.
it was pretty well known, or it's something new?
I'm not sure if anybody wrote it down, but it's well-known folklore, I'd say.
It's known. Maybe Etienne could comment on this actually.
Because you know exactly the minimizer.
Oh yeah, right.
Yeah, they
Yeah.
have to be conformal, so they have to be harmonic functions with Dirichlet boundary condition. They have to be constant.
Right. Yeah. Yeah.
Yeah.
I had it on the blackboard. I erased it. Minimizers with Dirichlet energy on a bounded domain are also minimizers on the whole space. But no, none of them have Dirichlet boundary data.
Okay. Other questions? Okay, well, I guess just a quick comment. I mean, you just want this to be zero, so which this expression in your integral, you want it to be zero more or less. So which means that you want them to be vertical. If you can find a place in the domain where you're vertical, you're happy. You stick in the skyrmion and you gain. But somehow, if you're not flat and you have a little bit of gradient, you cannot do that anymore. That what you pay is comparable to what you gain. And under certain conditions, for example, in a disk, there may not be a minimizer in degree other than 1.
Here.
Okay, let's say without any thought, if Q is 1, then there may not be a minimizer on a disk.
So okay. What you're saying is if you can replace Q bigger than 1 with just using the Poincare inequality.
Yeah.
And if you do that, that's also in our paper. If you do that, the estimates are not strong enough to conclude that any disk supports a minimizer. Because
other than degree 1.
Other than degree 1.
Yeah.
Because we don't. There exists a constant universal. We don't know what the constant is.
Right. Any more questions or comments?
I'm way over time.
Okay. If not, let's thank Theresa again.